Alrighty, so we're going to continue on with section 7.3, partial fractions. Again, there are a ton of examples in this section. So I think this is part, yes, this would be part 3, partial fractions. This is part 3. Okay, so we're just going to jump into another example. This one's going to be easier than the last one. So we have the integral dx over x squared minus a squared. And a is not equal to 0. So all that guarantees is that it's, when we do this decomposition, things make sense. So, okay, so we're just going to go through the partial fractions process, and it's the same as what we did last time. Step 1, factor the denominator. So we have x squared minus a squared is a difference of the difference of squares. This factors as x minus a times x plus a. And now what we're going to do is we're going to complete the so we're going to move on. We're going to do the partial fractions. So what we're going to do is we're going to take the factored rational function that we have. The denominator is factored. This was 1 over x minus a times x plus a. This is the integrand here up top. So the dx is 1 times dx. So this fraction here is going to be equal to a over x minus a plus b over x plus a for some a and b, which we have to figure out. So we're going to continue. We're going to do the same thing that we did last time. First thing we're going to do is we're going to put the right-hand side over a common denominator. And in this case, the common denominator is x plus a over, or sorry, x plus a times x minus a. So just kind of, I'm going to erase this in a second. But just to kind of highlight what I am doing here, I'm taking, this one and multiplying and dividing by x plus a to give me a common denominator. And the same thing with the x plus b. So I need an x minus a on the bottom, so I multiply and divide by x minus a. So that's what I'm doing when I'm putting this over common denominator. So that's more of an algebra thing, so I'm assuming that you guys have seen that before. So this left-hand side stays the same. This right-hand side, I put over common denominator. So I multiplied a by x plus a to get the common denominator, and b by x minus a. And the common denominator is x minus a, x plus a. So again, I now have the same denominator on both sides, so I can multiply over and they cancel. So what I'm left with is 1 is equal to a times x plus a plus b times x minus a. And now I want to take the right-hand side, and I want to write it as a polynomial in x. So x times something plus a constant term. Because this left-hand side is really 0x plus 1. So I'm going to make the right-hand side look the same. So I'm not going to worry about writing the 0x. We'll worry about that in a second. So I'm going to expand all these. I'm going to have ax plus capital A times little a. Yeah, sorry for choosing the same letter. Plus bx minus ba. Now I want to get all of the terms with x together. So I have ax plus bx plus capital A times little a minus big A, or big B times little a. And now I want to factor out the x's. So I'm going to get 1 is equal to x times a plus b plus capital A little a minus big A little a. And in this case, you have to be careful. A and B are my capital A and capital B are my unknowns. Little a is the part of the fraction, or the part of the denominator up top here. So it's assumed I know what little a is. So let's continue. So now I compare the left and right hand side. So this is where the 0x comes in. So if I look at, so I'm comparing the sides and saying these two polynomials are equal to each other. So that means the coefficient in front of the x here and the coefficient in front of the x here have to be the same. That tells me 0 is equal to a plus b. For my first equation, and my constants also have to be equal if these polynomials are going to be equal. So you get 1 is capital A, little a, minus capital B, little a. And now I need to solve this system of equations, two unknowns, two equations. I can do this. I'm going to do it the same way I did last time. So I'm going to multiply both sides by a, little a. If you're more comfortable with substitution, that's fine. This is faster. And so my equations now become 0 is little a, big A, plus big B, little a. And 1 is equal to, so let's rewrite the second one as little a, big A, minus big B, little a. Now I can add these two equations. So I get 0 plus 1 is 1. So capital little a, big A, plus little a, big A. I feel like I'm teaching second grade English right now. So that's 2 little a, capital A. And then these two terms cancel. So this is what I'm left with. And remember, I'm trying to solve for capital A here. I find capital A is 1 over 2 times little a. And now I can just plug this back into either of my equations. First one, so I'm going to plug it into the equation 0 is equal to a plus b. So that tells me 0 is equal to 1 over 2a plus b, or b is equal to negative 1 over 2a. So what was this all for? This was all because 1 over x minus a times x plus a was equal to a over, make sure I have these correct, a over x minus little a plus b over x minus little a. And now I know what a and b are, so I've already solved for those. A is there, b is there. So now I can just plug those in. And I don't know, so I know that these recordings don't come off the best. My plan is to start after this chapter, after this section, using a different method of recording these because they do come out choppy. So if the screen is going crazy, I apologize. But it should be b over x plus a. And so, okay, so I can rewrite, 1 over x plus a, so sorry, 1 over x minus a times x plus a as this, which is now something that's easier to integrate. So the idea behind this is the integral of 1 over x plus a, x minus a, dx is going to be the same thing as the integral of 1 over 2a, x minus a, minus 1 over 2a, x plus a, dx. Let me double check. Yeah, and I was just making sure that my work was all correct up until here. I wasn't writing down something completely wrong. All right, so now I can break this. So, okay, so now we look at this new integral that we can do that's equivalent to our old integral. And we say, okay, if I split this up into 2 integrals, so I can pull out the little a's, so the 1 over 2a factors. I'm left with these integrals. And these integrals are doable. Since the natural log of x minus a, natural log of x plus a, plus my integration constant. You can see that this process, even though it's kind of terrible, it does allow us to do these integrals in a much more, the integrals that we get are much simpler. So at the end of this video, I'm going to stop the video here because we're about to do we're going to see a new form of this, and it's going to take a little bit of explaining. So I don't want to start explaining it here and then have to start an example the next one. I'll start explaining on the next one. So I'm going to stop the recording here. This will be a short one, but nothing much to do about that.